All right, so this is lecture 10 for 124-104 Physics 1A. In this lecture, we're sort of still using some of the ideas we learned so far about an object's motion and force, but now we'll learn a new topic called momentum and impulse. Essentially, at the end of this lecture, we'll know what momentum is, what is impulse, and we'll learn another tool that we can use in solving motion for an object. So momentum, let's define what momentum is. Momentum is defined as mass in motion. So any object that has mass that's moving, we say that this object has momentum, and we use the symbol P for momentum. Of course, we already encountered velocity and mass. Velocity being a vector quantity, therefore momentum should also be a vector quantity. Mass is scalar, so whatever direction velocity is will be the direction for momentum. Okay. The unit for momentum will come from the definition, mass times velocity, the unit for mass being kilograms, and velocity, of course, meter per second. Okay, so since momentum is a vector quantity, we will be working with components just like we did with forces, right? Force is a vector quantity. So when we solve forces, we considered the components of the forces. So similarly for momentum, we will be looking at momentum along the x-axis, along the y-axis. So in this course, in linear mechanics, we'll really just deal with two-dimensional motion. So x and y components of momentum. But for completeness, momentum can also have a component in the z-axis if you're looking at three-dimensional motion. Okay, so knowing what momentum is, momentum being related to mass times velocity, the question is, how can we change an object's momentum? All right, if we look at the definition, we can change momentum by either changing the mass or changing the velocity, right? Okay, makes sense. Okay, you can change the mass. For example, if the object is rolling and as it rolls, it picks up some mud so that it becomes bigger, so it becomes heavier, the object's mass changes. Or as the object rolls, it sort of disintegrates, so it becomes smaller and therefore the mass decreases. So that's how the mass can change. In fact, in the third lecture of this week, we will see the effect of changing mass, but in most scenarios, the mass can be kept constant. Now you have a moving object. In most cases, the mass of this object does not change. So in most cases, the change in momentum will come from the change in velocity, right? And if you have a change in velocity over time, what do you have? What quantity, kinematic quantity, did we define as the change of velocity over time? Acceleration, very good. And if you have acceleration, then what should you have in order to have acceleration? Force, very good. Yeah, Newton's second law of motion says you will only have acceleration if you have a net force acting on an object with a mass m. Right? So in essence, yeah, this equation, this is the derivation of how force is related to the change in momentum, but essentially it comes from Newton's second law of motion. Force is equal to mass times acceleration. Acceleration is, of course, change in velocity over time. Mass, you can just include that there. And so you have the definition for momentum, mass times velocity. Therefore, force is equal to change in momentum over change in time. If the change is finite, we can just use this delta function, delta being final minus initial. This is for a finite change. If the change is very small and it's happening over a very, very short time interval, then this finite change delta becomes a derivative. So the force is also a derivative of momentum with respect to time. Okay. For most of our purposes, the change is quite finite. So in this course, we won't, we won't really be evaluating derivatives because, as I've said, derivatives, if the change happens over a finite time interval, then we can just simply use this relationship, final minus initial time. Okay, that's what delta essentially means, final minus initial. Right, but looking at this definition now, if I rearrange this equation, then we have, we'll use the finite definition. Then we can see that the momentum of an object can change by either changing the force applied on the object, okay, right, or changing the time delta t over which you apply the force on the object. So two ways of changing the momentum of the object. You either change the force applied on the object or change the time interval over which you apply the force. Of course, this time, the dependence on time comes, of course, from the definition of force being change in velocity over change in time. Right, simple enough. Change in momentum comes from change in force or change in time. Okay, but this is quite an important concept. In fact, it's important to have its own name. So impulse is the name that we use to describe how the object's momentum can be changed. So impulse describes how the object's momentum can be changed. In the previous slide, we defined that the change in momentum delta P can happen if you change the net force or if you change the time for which you apply the net force. And since impulse describes how the momentum is changed, impulse is then defined as net force times delta T. And we use capital J to indicate impulse as the symbol for impulse. Right, the unit for impulse comes from its definition. Impulse is defined as net force times delta T. It's because net force times delta T is how we can change the object's momentum. So the unit for net force is Newton, and the unit for delta T is, of course, seconds. So the unit for impulse is newtons times seconds. Or if you want to expand that further into base units, we know Newton is kilogram meters per second squared. This second squared cancels with the second here. And so you just have second to the minus one left. But yeah, newtons times seconds would probably be the easier way to remember the unit for impulse. Right, so bringing those concepts together, impulse being description of how the object's momentum changes, and the object's momentum changes by changing the net force or the time interval delta T. We have what we call this impulse momentum theorem, which just brings together those three quantities, right? The change in momentum is brought about by net force times change in time interval. At the same time, impulse is defined as the change in momentum. So these three quantities are all equal. That means you can use them any way you want. For example, you can find the impulse by taking the change in momentum, or you can also find the impulse by multiplying the net force applied over a time interval. Or you can also take the change in momentum by multiplying the net force over a time interval. Okay, so this is sort of how you use this double equal sign here. It just gives you three possible equations for you to use to solve problems regarding whether you are asked for net force or change in momentum or impulse. You just have more choices of equations to use to solve what's being asked. All right, all good so far? Still able to follow? All right. So in some cases, the net force that the force experienced by the object can be non-constant, so it can be changing. So for example, you have this ball hitting a racket. Because the racket is quite soft, the ball can sort of embed itself as it hits the racket. So you have this changing force over this time duration that the ball is colliding with the racket. And the change in force is described, for example, by this curve. So in this case, if you have a non-constant force, then the area under the graph will give you the impulse delivered by the force on the object. And in this case, the average force will be equal to the net force. Right, let's apply this definition, right? You have a non-constant force. To get the impulse, you need to get the area under this graph, but how is this all related to change in momentum and impulse? Let's look at this example. Okay, a hockey ball with a mass of 160 grams is moving with a speed of 20 meters per second, and it gives you the direction to the left. It is struck back by a defender at the speed of 40 meters per second. So you have initially a ball moving to the left, 20 meters per second. Okay, it's struck and it goes the opposite direction. Let's just put negative 20 for the left direction and positive 40 meters per second after it's been struck. Okay. Of course, it will move in the opposite direction. That's why it's positive. Okay, so given the model below, this figure here describes how the force changes over the duration where the hockey stick collides with the ball. Determine the maximum force on the ball and the average force on the ball. Okay. So maximum force, this is this point here. And average is, of course, some value between 0 and maximum. Okay. All right, looking at what's given in the problem, we can see that the velocity changed, right? From negative 20 meters per second, it changed to 40 meters per second. So there is a change in velocity, which means that there should be some change in momentum. So we can use this as one of the informations. So let me just write down what's given here. So we know the mass, 160 grams, 0.160 kilograms, the initial velocity, 20 meters per second, final velocity minus 40 meters per second. I think it's the opposite. Yeah, we did the opposite signs. So minus 20 initially, moving to the left. And then finally positive 40 meters per second. Okay, we learned in the previous slide, if you have a non-constant force, then net force times delta T will be equal to the area under the graph. Okay, when we mean area under the graph, just like in motion graphs, we mean the area between the graph and the horizontal axis. So it's actually this area that we want to find in order to find net force times delta T. Yeah, and the changing force, the non-constant force, is defined by a triangle. So you have there a 1/2 times base. Base is 60 milliseconds. Okay, don't forget the prefix milli. That means 6.0 times 10 to the minus 3 seconds. Okay, right? So a common thing, a common mistake I see is overlooking prefixes. this prefix milli should be expanded. So you have 6.0 times 10 to the minus 3 seconds for the time, which makes up the base of the triangle, and the height of the triangle is F max. Right? Okay, so the area under the non-constant force is 1/2 base times the height, which is F max. Right, this equation allows us to solve for the maximum force that the problem is asking, because that's F max, which comes out here. But for us to solve F max, we need to be able to know what the net force is over this time interval delta t. So delta t is this time interval over which the force is applied, 6 times 10 to the minus 3. But we have to figure out what the net force is. Right. There's a way of finding net force, because from definition, we defined that the change in momentum is equal to net force times the time interval, right? So if you have a changing velocity as seen here, that means you have a changing momentum. And by calculating the change in momentum, that allows you to find the net force. Okay. So change in momentum will be mass times the final velocity minus mass times the initial velocity. That will give you the net force times delta t. The mass is the same. It's still the hockey ball. Okay? And we assume that its mass, it did not disintegrate, and so its mass is constant. So then we can find the change in momentum by simply subtracting the final and the initial velocities. Remember, I use the arrows on top to remind us that we are working with vectors. And so when we do the calculation, we need to include the signs, the directions for the velocities. So your final velocity is to the right, 40 meters per second. Let me just also substitute the value for the mass here. The mass is 0.160 kilograms. Okay, times the final velocity is to the right, so that's 40, minus the initial velocities to the left. So you should include the negative 20, right? Because again, you're working with velocities, vectors, which should include the direction of the vector. So this will give you F net delta t. Right, well, we know delta t. Just let me go here. Therefore, F net is equal to 0.160. 40 minus 20 will give you 60 divided by 6 times 10 to the minus 3. Right? Cool. Correct. Yeah. Sometimes, you know, when I'm writing, my brain and my hand do different things. So if I write something that's incorrect, please do let me know. So therefore, if you just do the calculation, then the net force will be 6.4 times 10 to the minus, to the okay. Did someone try to punch these numbers in the calculator? But yeah. Okay, just you can check that if it's correct. Right. But once you've found the net force, you can then use that to get the maximum force. Therefore, so net force, maximum force will be equal to this whole thing, F net delta T times giving you a maximum force of 3.2 times 10 to the 6 newtons. Okay.
Wouldn't it be the opposite? Because they're dividing, basically the 6 times 10 to the 3 works out, divided by half, so you times by 2.
Yeah, this one will essentially cancel out. Oh, you're timesing by 2. Yeah, it's the opposite. .4 times 10 to the 3 for your net force. Yeah, there's something wrong with this, yeah. Is this net force correct though? This should be 1600. Yeah. Okay, let's see. 0.6, 60. Uh, 0.6 times 60. Yeah, 1600. Yeah, yeah. Okay, so that will then change this. Okay, 1600, so this will be 3. Yeah. That will be 3,200, which is times 10 to the 3. Yeah. Cool. Right. Okay. Cool. And we want the average force as well. The average force is equal to the net force. So average force is also equal to the net force, which we've calculated here, 1,600 newtons. Okay, so this example shows us how we can use the graph of a non-constant force to find either the maximum force or the average force or the change in momentum impulse. All right, let's look at this other example where we're now looking at just a scenario and we assume that the force exerted is constant over the time interval. So you have this car with a mass of 1,500 kilograms. It's moving to the left. So you have this negative 15 meters per second. Again, we're talking about vectors, so you have to include the signs. It hits a wall at this speed, 15 meters per second, and rebounds to the right. So after it rebounds, of course, it's moving in the opposite direction. And so you have this positive for the direction the speed was given. So the first question is, find the impulse delivered to the car during the collision with the wall. So impulse describes how the momentum of an object changes. We can see here that the change happened in terms of the change in velocity. Okay, so the velocity of the car changed. Therefore, impulse will come from the change in momentum. The change in momentum coming from the change in velocity. So some signs missing here. So we need to get the change in momentum. We need the initial and the final momenta, right? So the initial momentum can be equal to mass times the initial velocity. Right? Mass of the car is given times the initial velocity should be negative 15 meters per second because your car is initially moving to the left. And so you have a negative 2.25 times 10 to the 4 kilograms per meters per second. For the final momentum, this will be the state after the collision where the velocity of your car has now changed to 2.6 meters per second to the right. Therefore, you have the mass of the car times the final velocity. The mass is the same. We assume no parts of the car are thrown away because of the collision. So mass times the velocity, we're moving to the right, so you have a positive velocity giving you a positive momentum. 0.390 times 10 to the 4 kilograms meters per second, which means positive means your car is moving to the right. The impulse, therefore, is the change in momentum. So this will be the final momentum minus the initial momentum. So we simply subtract these two final 0.390 times 10 to the 4 minus negative 2.25 times 10 to the 4. That's 0.3 will give you 2.64 times 10 to the 4 kilograms meters per second. Right. And if the car is in contact with the wall over this time, 0.150 seconds, find the average force that the wall exerts on the car during the impact. So we know the momentum. The momentum impulse theorem says that the impulse is also equal to the net force times the time interval over which the force was applied so as to change the momentum of the object. So we've calculated the impulse previously. That will allow us to find the net force, which is also equal to the average force. That's equal to momentum, the change in momentum, 2.64 times 10 to the 4, divided by the time interval, 0.150 seconds, will give you this average force, which will be positive, because your impulse from before is positive, meaning your change of momentum and impulse from before is positive. So your average force exerted by the wall, the force exerted by the wall on the car will be positive. And if you think about it, it makes sense because the wall exerts a force to the right on the car. So you should have a positive net force in this case. How about if we ask, what's the force exerted by the car on the wall? So a follow-up question, what is the force average force exerted by the car on the wall. What will that be? Or how much? How much if the wall exerts an average force of 1.76 times 10 to the 5 newtons, how much average force will the car exert on the wall when the car hits the wall? What does Newton's third law of motion say? Yep. So the amount of force exerted by the wall on the car should be the same amount as the force exerted by the car on the wall, except that the direction will be opposite. So you'll have a negative 1.76 times 10 to the 5 newtons. Right. Okay. Right, so let's consider these two objects. They're two hard balls. They're approaching each other. One has mass m1, the other has mass m2. M1 is moving to the right with this initial velocity v1, and mass m2 is moving to the left with this initial velocity v2. They collide, after which they sort of bounce from each other, and they're traveling in opposite directions after collision. So the impulse delivered to the objects M1 and M2 will be due to the forces that each of them exert on each other. Just like the example we've seen here, the impulse delivered by the wall on the car is because of the average force that the wall exerted on the car. So we can use the same argument and say that the impulse delivered on mass 1 will be the force on mass 1 because of mass 2 times the time interval, and that changes the momentum of mass 1. Okay, so it's just some notes on the indices here. So 2-1 means it's the force by 2 on object 1. So the first number here, the first number in the index means it's the object that's exerting the force, and the second number in the index means it's the object that's receiving the force. So F21 means it's the force by mass 2 on mass 1. The force exerted by mass 2 on mass 1 over this time interval changes the momentum of mass 1. In the same way, the force exerted by mass 1 on 2, okay, the force exerted by mass 1 on 2 over the time interval delta t will change the momentum of mass 2. Right. Okay, we've seen from the previous example and Newton's third law, the force exerted by mass 1 on mass 2 should be the same magnitude but opposite in direction compared to the force exerted by mass 1 on mass 2. Right? So these two forces here are equal, but they're opposite, and so you have this negative sign. So if I expand Newton's third law of motion using the change in momentum, so F21 we define as the change in momentum of mass 1, so M1v1F minus M1v1I, right? Final momentum minus initial momentum. Final momentum minus initial momentum. Okay. For F12, okay, it will come from this definition, except that you have a negative sign. So M2V2F will become negative, and M2V2I will become positive because you have this negative being multiplied with this other negative. So you have this positive M2V2I. But still, you're talking about the final momentum of mass 2 and the initial momentum of mass 2. Let me just put indices here to know we're talking about mass 1 and mass 2. Okay. Now, I just rearranged this equation here so that I collect on one side all the initial velocities. So on one side, I have initial velocities, and on the other side of the equal sign, I have final velocities, right? And I just, yeah, so I have this equation here, which I just copy over to the next slide. So I copy that equation over to the next slide. You have initial velocities on one side and final velocities on the other side. This gives us, we can then define that on the left side will give us the initial momentum and the right hand side will give us the final momentum. So if you see here, this is the definition for momentum, initial momentum for object 1. This is the initial momentum for object 2, the final momentum for object 1, and the final momentum for object 2. So the total initial momentum is the sum of the initial momenta of the objects, and the final momentum is the sum of the final momenta of the objects. And we can see that they're equal. So P1, PI1 plus PI2 equals PF1 plus PF2. This means that the initial momentum of the system is equal to the final total momentum of the system. And this is what we call the conservation of momentum. Okay, yeah, because the total initial momentum is equal to the total final momentum, even when objects collide. Their momentum, the total momentum does not change, therefore momentum is conserved. So conservation of momentum says that the initial momentum is equal to the final momentum. If we think about momentum as a vector, this means that the x component of the total momentum before and after is constant. The y component of the total momentum before and after is constant. And if you are looking at 3 dimensions, the z component before and after a collision should also be constant, the total momentum. Right? And the conservation of momentum, just like conservation of energy that we learned in our last week when we talked about energy, power, and work, gives us a powerful means of calculating the velocities, the resulting velocities of colliding objects. And we'll look into that in more detail in the next lecture. But we will look at one example now just to see what conservation of momentum means. Right, so here's an example. A fireworks box has a mass given here. It slides with a speed 4 meters per second across a frictionless floor. Okay, that means we are conserving energy at the same time as momentum. So the speed is 4 meters per second in the positive direction. In essence, the velocity is positive 4 meters per second. It suddenly explodes into 2 pieces. One piece has a mass of 2 kilograms, which moves in the positive direction with this speed, meaning the velocity is also positive 8 meters per second. And the second mass also moves along the x-axis, but we want to find what's the velocity of the second piece, which has a mass mv. All right, have a little think about the scenario. It's the same problem here. Just while I write down what's given in the problem, okay, we're given the mass of the box. I'll just say that this is the total mass m, 6 kilograms. Okay. So you have this box. With mass m, it's moving with some velocity to the right. Okay, then it explodes into two pieces. MB and MA. Okay, the problem says they both move along the x-axis, but mass A has a velocity A that was given. We want to find the velocity of the second piece. Right. So the mass of the box before it explodes, it's given to be 6 kilograms. The velocity of this box is given to be 4 meters per second. It's moving in the positive direction. So you have a plus 4 meters per second for the velocity of the box. It then explodes into two pieces. You have piece MA and piece MB. Piece MA was given to have a mass of 2 kilograms, and piece MA was given to have a velocity of plus 8 meters per second. We want to find the velocity of piece MB. First, are we able to figure out what's the mass of piece MB? Yeah. Right, we assume that the box just splits into two and there's no shrapnel that's flying around. Then the total mass of the two pieces should add up to the total mass of the box. Right? So we can assume that for simplicity, so that the mass of piece B should be 4 kilograms. Right. Okay, so we have two scenarios here. One is before the explosion and the other one is after the explosion. If we use conservation of momentum, then that means that the total initial momentum before the explosion should be equal to the total final momentum after the explosion. Right. So we're looking at total quantities, not just at the individual quantities of the boxes. But before the collision, you only have one object. So the total initial momentum will be the momentum of the box. Okay. Will be the momentum of the box. Okay. And afterwards, that will be mass times velocity of the box. Okay, but afterwards, you have two pieces. Therefore, the final momentum after the explosion should be equal to the momentum of piece A, final momentum of piece A, plus the final momentum of piece B. Because after the explosion, you now have two pieces, and in conservation of momentum, you are looking at the total momentum. So you have to add up the individual momenta of each piece. So this will be mass of piece A times the velocity of piece A plus mass of piece B times the velocity of piece B. Conservation of momentum says that these two should be equal. Right? And so MV should be equal to MAVA plus MBVB. Right. We essentially want to know VB, velocity of box B, and we know everything. We rearrange this equation for the velocity of piece B. That will be MV divided by minus MAVA divided by MB. Right. VB, so it's now just a matter of substituting all the numbers. Mass is 6 times 4 minus 2 times, so I'll just put brackets, 2 times 8 divided by 4. Gives you a velocity of positive 2 meters per second. The positive sign will tell you in which direction the piece B is also moving. It should also move to the right. So you also have this velocity to the right. Right. Cool. Any question about this example? So with momentum problems, one thing to look out for is whether there is a before and after moment, like before a collision or after a collision, before an explosion, after an explosion. If there is a before and after moment, then almost 100% of the time, conservation of momentum gives you a powerful tool in solving one of the unknowns. In the next lecture, we will look at different kinds of collisions, but you can look at this exercise to practice how to solve the impulse being related to the change in momentum. And yeah, I think, yeah, conservation of momentum if you need to find some other quantities. So I leave you with this exercise. Depending on the time, we can look at the solution next time. But if there are no questions, then we'll end our lecture here, and I'll see you tomorrow. Have a good day, everyone. You're welcome.